Thank you. So I'm going to talk about TypeScript. I'm going to talk about types. But for those that don't know me, I'm the head of development in Sorosiko, Macedonia. I've been coding professionally for 2 millennia now. I love programming. I love programmers as well. And my professional passion is basically building better programs and building better programmers. So this will be a bit of both, I think. My relationship with JavaScript in Facebook terms is it's complicated. So sometimes I love it, sometimes I don't, sometimes it loves me, sometimes it doesn't. But on the other hand, as soon as TypeScript appeared, we started a long and fruitful relationship. And to be honest, I'm one of the very few guys who had TypeScript 0.5 running on production. Don't tell that to the clients. So what will we talk about? I will talk a bit about the history of JavaScript, a bit about the history of TypeScript, and then we're going to talk a bit about types, and we're going to have lots of demos. So let's do the history part. JavaScript was initially designed for non-professionals, for webmasters, not for web developers. There was no such thing as a web developer back then. And it's trying to be as nice as it can be for non-professionals. Tries to guess what the user actually wants and not what the user actually wrote, which is great for non-professional users, and it kind of sucks for us. There were differing standard implementations. Everybody was doing their own thing. There was no security, no safety, and one of the reasons that it's called JavaScript was it was intended basically to glue together small bits of things between the huge Java applets that were supposed to run the internet. That didn't happen. So right now, JavaScript is the language that powers, well, everything. But the debugging experience in JavaScript was never quite good. A lot of the time, we would write some code that we would think that it does one thing and it would do something else. And one of those issues was with some of these. These are a list of things that I hate or hated about JavaScript. Implicit globals, variable hoisting, whatever the heck is the truth and false things are. Semicolon insertion, which was very fun if you come from a .NET world where that was basically the default way of doing this. Whatever this is, yeah, I know the full definitions and I still think it's absurd. There was this beautiful thing called type coercion when you get a string and then you treat it as a number, which is then treated as a string, which is treated as a Boolean, and something happens. It has no type whatsoever, one of the very few languages when you can say, well, this thing is a string, but now it's a number, but now it's a record. It had prototypal inheritance. Nobody knows why, including Brendan Eich, the guy who invented JavaScript. And the asynchrony model was kind of weird for the time. But there are also a few things that I loved about JavaScript. JavaScript, from the very first version, had first-class functions, which means functions were things that you can use as variables. Functions are things that you can pass as parameters. Functions are things that you can get as return values, which means that JavaScript could be used in a somewhat functional manner. Because of that, it was extremely extensible. We talked before about all of the frameworks that are built on top of JavaScript. Most of the features of those frameworks are kind of impossible to do in a more structured language that will constrain you more. So it was infinitely extensible and infinitely malleable. You could do a lot of things to using JavaScript to JavaScript itself that people got by, basically. Another thing I loved was prototypal inheritance, because when it worked really great. And you were able to do some silly things that are just not possible in proper languages like C# or Java, and the asynchrony, unlike in most of those other languages, actually worked. So we were able to use asynchronous development without totally breaking our minds. Now it's better. And I'm going to mention first-class functions again because they're just that awesome. And what happened then? Well, then TypeScript came along. And who here has been a web developer or any kind of developer before 2015? You remember the JavaScript of then? It was a scary thing. Yeah. So I'm going to assume that most of you have actually seen some JavaScript and some TypeScript, but let's just show. Here we have a TypeScript example. You can see all the way in the back? Great. We have some code, some methods, some function, and this works. I'm not going to run it. It doesn't really matter what it does. But let's see what happens when I transpile this to an ultra-modern JavaScript. Let's take a look at that. Here it is. Let's compare them. So we have TypeScript and we have JavaScript. Totally different languages, nothing in common. Sorry. Yeah, you can see that there are a lot of differences between the modern TypeScript and the modern JavaScript. Namely, it has used strict, and then it went ahead and removed this part, which is the type. So right now, TypeScript and JavaScript are more or less equally awesome aside from the types. So types are a kind of a mixed blessing, so to say. I am a huge fan of types. I mean, it shows. But there are a lot of people that say, I don't like types. So at this moment, that's quite okay. If you don't like types, you can use this. If you like types, you can use this. There's not much difference between modern TypeScript and modern JavaScript. And that's one thing that people kind of forget about TypeScript. That TypeScript drove the development of modern JavaScript so that right now we have a very nice, very good language that we can actually use. Without types still, but it's usable. On the other hand, and this is what I'm about to show you is not completely representative because you just cannot compile to the version of JavaScript that existed in the 2013 or something like that, but this is as close as it gets. So this is what we need to get this code to actually work in the JavaScript of yesteryear. That's a lot of code, and that's a lot of kind of complicated code, right? Yeah. Do you want to write the code on that side? No, nobody does. That's why we invented a compiler, a transpiler to actually do that. But right now, if you really, really don't like types, I'm just going to say, don't use TypeScript. Use JavaScript. It's equally awesome. But if you do like types, then we can move along. Yeah, let's see what these things are all about. So let's start with the basics. You know, TypeScript has things that we call interfaces and types, which are kind of equally powerful, and nobody understands why we have two of them when what would have been enough, but we have two of them. We have function types, where we can type a function using a specific type, which is quite common in all functional languages. And we also have this thing that we call union types, or discriminated union, which a lot of people are not using as much as they should because they're immensely powerful. And they can provide a lot of value without too much hassle. So, let's see what we have here. So, for example, the first definition, you know, the colon, the type definition, that's a number. I don't even have to do that. Num is a number, but even if I remove the type annotation, TypeScript has an extremely powerful type inference thing that now it's, well, num is actually 3. But we can define it as a number as well. First name, that's a string. Last name, that's a string. And then we have a person, which we didn't type anywhere, but TypeScript inferred it that this is a thing that has a first name, a last name, an age, and an email. And we can use all the JavaScript nice things that we have, and TypeScript will correctly guess. So I deconstructed that, and now it knows the age is a variable that is of type number, and the rest is a variable, or a constant, of this type. Age is gone, magically, because TypeScript inferred that we removed it from this thing. And, of course, then we can define a function, and let's see what the type of this thing is. So it automatically detected that this is a function that will take a number and return a number. And that is the type of this function. And we can use that type to actually create other functions and do whatever we want. And moreover, it detected that the result is a number. I never said that the result has some specific type. Similarly, we don't have to do a numbers with numbers, but here we have that it takes two numbers and returns an object that has a property called result, which is a number. And of course, the result itself will be an object that has a property called number. So, this is another example. So here we have the response status type, which is a discriminated union of two different types, and those types are literal values. So the only two possible values of the result status is the string success and the string error. Everything else just doesn't work. And then we can have an interface like this. Is this a good thing? Can we make it better? Sure we can. So, what is the problem with this? If the response is successful, what should be the value of the error? Well, it's going to be undefined. But if the response errors out, what should be the value of the payload? Well, it shouldn't be. So let's go that way. We can do some things like this. So now we have two types. And the first type, the status is literally the literal success. And that thing will have a payload, which will be generically typed to T, and it will have a message, and we're going to have an error response. And how do we declare the response right now? It's complaining that it doesn't have a response. Well, that's simple. We're just going to say, we're going to have a type that's this. We have a response that is either a success response or an error response. And now the code itself, because TypeScript also has a lot of type guards, if we know that we have an error response, we cannot access the payload. Accessing the payload would be a mistake, because an error response doesn't have a payload. And note that previously the error was optional. No, right now it's not. The error response will have an error, because it's an error response. Similarly, the success response does not even have an error property that we can access. Because the easiest way to avoid having a bug is to remove the possibility of the bug. So if right now I have some objects of the type response, I just cannot say this doesn't work. Why? Because I don't have an error property. I mean, it's obvious. But JavaScript would say that this is okay. And this is a simple trick that we can use to actually model the responses, the world, according to what it actually has. So we don't have a lot of types or one single interface with 70 properties, and most of them are optional because it covers different scenarios. We can have interface per scenario. And then we will be able to use it as it's supposed to be used. Of course, the same goes for the error response. Additionally, you can go overboard if you want to actually take out the message and the status into a base class, base type. That's fine. If you want to, you can. For one single property, it doesn't make sense. If you have multiple properties, sure it does. So that's an option as well. And here we have type intersection. So we are saying that the success response has all the things that the base response has in addition to these properties. So everything else will work just as fine. Again, if we just have a status and a message, this doesn't make sense, but if we have 15 properties, this will make sense. Because now if I add something to the base response, automatically everybody has it. Additionally, sometimes we want to use enums and things like that because they're useful. But this is really not JavaScript code that we want to write. This is not in the field of JavaScript. What is in the field of JavaScript is this here that we're going to use the string left. But how if we put in the string left, which is the actual value of the directions enum left, no, it's an error. What can we do? We can actually create a type from an enum. We can just say and one more thing, I'm going to be using this format a lot. This means that I'm declaring a function with this signature, but no, I'm not providing the implementation because that's JavaScript and that's boring. So we're going to define a type that will allow us to do it in the JavaScript way. Yeah. So what does this mean? It means get the type of the directions enum. And that type is basically this. And then get a list of all those of the keys of that type. What are the keys? Well, the keys are basically the strings, left, right, top, and bottom. And let's see now what happens. The directions types is actually a union of those keys. So now, if instead of directions enum, we just say direction, here we can actually use left, which is in the spirit of JavaScript, because that is how we want to do it. Okay, this was some, let's call it basic things. Let's go a bit deeper. We kind of shown the generics, but we'll see a bit more of that. We show what key of is basically it gives us all the keys that are present in a certain type. And we're going to talk about my favorite type, never. My second favorite. My favorite is unknown. So, never is a type that never happens. How is that useful? We'll see. So let's go to another demo. Well, a common thing that happens is that we need functions like this. We have an object, Weko, and we want to send it to the front end, but we don't want to send the password. Yeah, if we do that, Boże will be mad at us. Yeah, and he's going to use this as an example of one of his next talks. So we're going to omit password from Weko. And this is the type. What will be now the type of Weko without password? It will be any. And that's just not nice. Basically, this method, the signature of this method will turn directly, indirectly, TypeScript into JavaScript. If you want to write TypeScript, say that you're writing TypeScript, but not actually do any typing, just put any everywhere, and you're golden. But let's not do that. So what we want to do is actually to have nice typing. So I will say, can this be any object? Yeah, but it can be of type T. Yeah. So this is better. And can the key be just about any string? No, it should be one of the properties of the T, right? Those are the only valid values. If I say remove Weko's car, Weko doesn't have a car. You cannot remove it. This should be an error. So we're going to say that this thing is going to be of type K. But what is K? Well, we're going to say that K is actually any type that extends the type that includes the keys of T. And now, this was an error before, because TypeScript didn't see an error problem with this line, but now it knows that this line is wrong, because Weko doesn't have a car. And it also knows that this line is correct, because does Weko have a password? Yeah. And one other great thing for development experience is when I go here, I cannot enter anything that's not a known property of Weko. That's great, but again, Weko without password is something. And we want it to be better. So actually, let's change this a bit. This is a very, very similar method that does the opposite. It only takes what we specify. So again, we're going to have something like this. And that thing returns any. Actually, I will say, why not return another type? Let's call it QWE. That will have to take T and K as parameters, right? And we'll define, we have something like this. Or we can just say, well, you are another way to say any. Kinda seems that we're on the right track. Well, let's rename this. We will call this a pick type. And what will be the properties of that pick type? Well, we're going to say that. We're going to say, thank you, Copilot, since K is actually a discriminated union. K is a set of strings that we provided. For each value in that, so we're going to run a for loop, kinda, sorta. For each P in K, for each property name in the list of keys, set a property with the type of T of P. Since T is the original type, so T is person, K is password, or let's say password. T of P says the type of the property password that's included in the type Weko, which is a string. But it will only do that for those keys that are present in K. So only the keys that are present in the list that we gave it. So let's see what happens now. So we have this call. We are picking from Weko, we are picking the first name and the last name. And again, we have that behavior here, that we are only allowed to use what we are allowed to use. I cannot seem to find where the semicolon is on my keyboard. But name only will now say, sometimes it wants to play smart. If we actually do this, name only right now is an object that only has two properties, the first name and the last name, because those are the two that it picked out from the bigger object. So if we want to just to get some properties, we can use pick. But if we want to use everything and just omit something, we're going to need to do something else. And I will paste this for the interest of time. Yeah, now it's getting complicated. Now we want to do the opposite. We want to take everything that is not mentioned. So if something is mentioned, don't take it. So instead of doing K as we did before, we're going to do all of them. But we're going to add a filter. So this is in effect, if we were working with a JavaScript object, we would say filter those that are unequal. So take all the properties in the type T, loop through them, and change them to this. What is this? This you've seen. So this part is a conditional type, so-called. So this is a type that will check something and return, if that thing is true, will return one thing. If that thing is false, it will return something else. So if the P extends K, that means if that property is in the list of property that we mentioned, if it's the one that we want omitted, what do we want to return? Well, we return the type never. So that thing, that property will have the type never, which means it doesn't exist, which means it won't be included. Otherwise, so if that P is not in K, return P. It just passed through. So this is for things that are not in the list, this is an extremely complicated way to say P. And it has the same type. So this will list all the properties except the properties that are in K. And if we say that this actually returns this type of variable, let's see now. Weko without password is something complicated, but if we do this, yeah, these are all the properties that Weko without password has. So it has age, it has email, it has first name, it has last name. Password is gone. We received another object that just doesn't have the password property. And that is statically known. I mean, to actually not have the password property, you will have to do the JavaScript that removes it. That's as well. But type-wise, this is now an object that doesn't have the password property, where if you access the password property, it will say, this is an error. And once more, you can only remove the properties that this actually has. So this will also return a runtime compile error because Weko doesn't have a car or a yacht. Any questions so far? Or is this clear? Because we're going deeper. So, we talked about conditional types, but sometimes we also need to declare some kind of, let's say, variables. Conditional types provide us with the if statement, so to say, when we're doing types. But sometimes we might want to do some pattern matching and extract some values and things like that. And this is where infer comes along. So, one thing that's quite popular right now is signals, right? So let's create a method that will, given an object, will transfer it to a signalized version. So we have this person, and then we want to do this method, and we want signalized person right now will be just about anything. What we want this to be, we want to have something like this, not signed from crypto. We want this signalized person basically, so the first name needs to be a function that will be a getter. We need to add another function that will be set first name or something like that. How do we do that? Well, quite easily with map types. Oh, no, that's the next example. But we're going to say for each this, well, this is just a simple thing, so it's going to be a method that returns the type that we have. And we're also going to add another set of properties. Yeah, something like this. I wrote this a few times in the last couple of days, so this thing knows. So what does this mean? That for each property, replace that property with a function getter and add another property, but only for the properties that are string, because technically properties can be numbers and symbols as well. So I need to add this. And now if we go to the signalized person, let's see what properties does this thing have. It has age, which is a function that takes nothing and returns a number, and then we have, oh no, age changed. I wanted to have set. Not changed. So now this will have set age, set email, set first name, set last name. I don't like this. I mean, it's okay. This is a function that takes a string or a number and returns void. But I would love if this was actually with a big letter at the front. Yeah, this is much better, right? So we were able to signalize that. Or another version. So I'm going to switch over to the ready-made thing. Another way that we can do this is to basically add an on method that will only take, for each property, it will only take the name of that property with the changed added, as age changed, anything that, and we'll have a specific listener that we can attach. So this is modeled in the correct way. And this kind of scratches all the things that we can do with TypeScript. And here we have another fun example. So, we want to have a method that accepts a string, but only if that string is a valid URL. Can we do that with typing only? Sure we can. Yeah, that's an error, that's an error, that's an error. How do we do that? Well, it's kind of simple. So we have this type that says, take in any T that extends this pattern. The pattern is, we have a scheme, which is a type at the top, and the domain, which is the type under that, and then take all the rest. And since we use infirm, we actually take that as a variable. And then we say, if the rest is a valid URI segment, then that's true. If is valid URI segment of rest returns true, then return T, otherwise return never. So if we have an error and our string is not a URL, we have an never type. And is valid URL segment is actually quite funny, because we have the type itself used as in the type definition. So that's a recursive type. What it does, it will actually take the values character by character. It will check the first character and recursively call itself on the next one. So it will check all the characters, and this type will be true if it's valid or false if it's not valid. So basically, we can check if something is a valid URL. And another thing, yeah, we have more recursive types where we can define a whole deep thing as a read-only. We can have a type that checks nested properties, or we can, for example, re-implement how things are capitalized using the infer within the type system. So this is not really too useful, to be honest, if you know this, but it's good to understand it, because if you're doing a library or you're writing code that somebody else will be using, you need to make it better for them. You need to make them have a great developer experience. And this is an awesome way to do that. Those things with infer and everything, I didn't get it right on the first try. Claude helped me quite a bit. But once you get it right, the developer experience is immensely better, because a lot of the time people just cannot make a mistake using that. They are forced because they put a quotation mark and out pop the 3 valid values. That's about that. So we went overboard already. Any questions, any comments? Of course, the code is over there. The presentation will be uploaded as well. Yep. In principle, no, but there are basically repos on the internet when you can find examples that will break the compiler. Basically, you can force it to go into an infinite loop, or you can make a type that only evaluates to true if the Fermat theorem is correct, or something like that. You can make that, but it's really not easy. For most, I would say, all normal scenarios, it's reasonably fast.
Other questions? No, there is no questions.
No, we are just 10 minutes out of bounds.
Give her an applause to Veko.